Okay, so we've got the circle, which you understand the 20 pi bit?
Yes.
Right,
That's
so
the perimeter for the whole circle.
A sector, basically you have to work out the fraction of the whole circle. So the fraction is this angle
Over 2 pi.
over 2 pi, because the whole thing is 2 pi. So we've basically got, it's 1.2 radians out of 2 pi radians, and then you multiply that fraction by what you're trying to work out. So if we're trying to work out the whole perimeter, it's multiplied by 2 pi r. So it's the circumference, yeah?
Okay, yeah.
You're okay with that, yeah? Get rid of that, because it's...
Wait, so 1.2 over 2 pi, what does that figure out? That's just...
That's just... So this here would work out that, because that arc length is a fraction of 2 pi r.
Oh, so 1.2 over 2 pi is for the length.
So that is the fraction. So, for instance, if I wanted, which isn't in this question, if I wanted to find the area, I would do 1.2 over 2 pi, because that's the fraction, times pi r squared. If I want to find part of the circumference, I would do 1.2 over 2 pi times 2 pi r. Okay. So what I've done is I've done...
Oh, that's the formula.
That's the formula,
Oh,
yeah.
okay.
So it's a fraction of... So this is sector area, and this is arc length, because arc length or sector area is a fraction of the entire circle. So that's why it's that fraction of the entire circumference. So basically then I am going to do circle subtract arc, and that leaves me with what's left. Okay. So circle, the circle is 2 pi r, and then I subtract 1.2 over 2 pi times 2 pi r. Okay, so that's circle and that's arc length. Make sense? So now I've just got to put the values in. So 2 pi r is 10, so it's 20 pi minus, well, it's 1.2 times 2 pi, so divided by 2 pi times 2 pi r, so the 2 pi's cancel, so it's actually minus 1.2 times r, which is 10. Okay. Which is then 20 pi minus 12. But that is only the circumference of the circle that's left, the major arc as we call it.
Yeah.
So the major arc, we should put it in a different colour, so that's this bit here.
Yeah.
Right? So that's where it's at. So what's missing?
Hello, sorry, is Adriana here?
No,
She's HR maths.
yeah, she's next.
Next one.
So what's missing? Yeah, exactly. It's this and this. So we've got to do what?
Is that just 10?
But both of them are 10, aren't they?
20.
So we've got to add 20 on. So our final answer is 20 pi plus 8. And that's it.
Oh, you don't simplify it? Or you can't?
Well, you can't simplify it, actually. You can't simplify that.
Oh.
Yeah? So that gives you the whole thing, I think.
Okay.
Yeah? Okay, question 3. So, the hence or otherwise bit makes you think, well, I should use, and the clue is this. So, 2 to the power of 3 is 8. Yeah? M is 3.
Yeah, M is 3, yes, yeah.
And that's even easier then, because you just understand that it's 2 to the power of 4 equals 16. Alright? Now, it says hence or otherwise, so we're going to be using this. It's like, oh, right, okay, 8, 16. So why not do what it's suggesting, which is, it's 2 to the power of 3 to the power of 2x plus 1 equals 2 to the power of 4 to the power of 2x minus 3. Alright? And what do you do with powers either side? Multiply them. So I've got 2 to the power of 6x plus 3 equals 2 to the power of 8x minus 12. And when you've got the same base with different, well, the same base, the powers have to be equal. So now I can just do, well, 6x plus 3 must be equal to 8x minus 12.
Oh, that's so simple.
It is, and it will be. So now I just solve, take 6x, gives me 2x, add the 12, gives me 15, which makes x 7.5.
What did I even do?
Okay, so all this is about is understanding functions and function notation and the link. So for instance, find f to minus 1, that's the inverse, yeah? So we know that x goes in to a function, f of x, and out comes y. So if y goes in to the inverse function, we get x. Alright, it's the same numbers. So that means this notation means what's x. So I've got to put minus 1 into the inverse function, which basically means minus 1 goes here. What's x? So this is f of x. So instead of doing x minus 1, all I've got to do is look for when y is minus 1. So y is minus 1, go across, there it is. What's x to give that value? 5.
Isn't it what? Well, you remember, Mark, if I told you that I got something else and you kicked it? Because I put 2.
Okay,
So I did where x, so where y is minus 1.
Yeah, so you're looking at when it's inside the brackets, it means that's the input. What's the output? So the input into an inverse is the output of the original function. So I put minus 1 into the inverse to get the output. That what that means is, what is the input into the initial function that gives me minus 1? So I look at the y, minus 1, read across, okay, and I get the answer 5. So the inverse of minus 1 is 5. Okay. So what does this mean then? The function of minus 1. So that means apply this function twice. So it seems like, I don't know, how am I supposed to do that? But actually it's kind of obvious in that, first of all, I put minus 1 in, I get the answer 2. So f of minus 1 is 2. And then what you've got to do is apply the function to 2. So f of 2 equals what? And that is also on the graph. So 2, the answer is 1. Yeah?
Oh, right.
Yeah, so that answer is 1.
So the complete answer is 1. So f of s of negative 1 is 1.
Yes. So it's kind of using the graph twice. Now obviously that would be an issue if the answer to the first function was outside. I couldn't use it again, you know. But with this graph I can, you know, it's easy enough to do. Right? Does it make sense? So that's actually it's about the fundamentals of functions. What goes in, what comes out, you know, reading the graph. So I think what a lot of people think, which obviously you guys all, well not all of you, but a lot of you have in this class, is you still think of graphs as a separate topic to functions rather than another way of reading functions. It's just the same thing, but I also think that's probably the way that you've been taught, is to think of it as separate things. We do it separately rather than together. But anyway, so on the same diagram, f of minus x, you just need to realise what kind of transformation that is. So it means whatever x is, give that answer as the negative value.
Do you
For
reflect
x.
it on your y or the x?
Well, so what it means is, if you look at f of x,
Yeah.
work out the answer, but apply that answer to minus x. So for instance, when x is, let me just change colour. When x is 1, this is the answer. So put that answer when x is minus 1. Yeah? 0 stays where it is. When x is 2, this is the answer. So put that answer for minus 2. When x is 3, put it as minus 3. When x is 4, put it as minus 4. So you end up with a reflection, yeah, in the y-axis. So we end up with a nice curve. So it looks like that. Some people just thought, oh, it's going to be a reflection in y equals x. And why do we think that? Because a reflection in y equals x is when you have when you're looking at the what?
When it's to the minus 1, right?
So the inverse. Yeah, so the inverse function is a reflection in y equals x. So if you were asked to sketch the graph of the inverse, you'd have to reflect it in y equals x. Right?
So wait, so if you do
What would yours be, Noah? You've reflected in the x-axis.
Yeah.
So that would not be f minus x, it would be what? That's just the same thing. So if y equals f to the minus x gives a reflection in the y-axis, does anyone know what would be a reflection in the x-axis?
Negative f of x.
Yeah, exactly. Negative f of x. Because what you've done is changed all the y coordinates to negatives. So that's another way to think about it. So this one, change all the x coordinates to negatives but leave the y the same.
Yeah.
This one, leave the x's the same but change the y coordinates to negative. That's another way to think of it.
90 or 180?
Yeah, obtuse angles are like this, aren't they?
Yeah.
More than 90 degrees. So, when you're asked to sine x equals 3 over 4, the first thing you should think about doing is drawing yourself a little triangle, right angle triangle, to work out everything you can. So you're told that sine of x is 3 over 4. Now you know sine of x is opposite over hypotenuse, yeah? So therefore, if this is theta, the opposite side is 3, the hypotenuse is 4. So what we could do is work out the other side. That would always help.
Okay.
So what is the other side? How do we work it out?
X squared plus 2 squared equals 4 squared.
So we've got 4 squared minus 3 squared equals the one I want squared. Pythagoras' theorem. So I've got 16 minus 9 square rooted, which is the square root of 7. So we've got square root 7. Alright. So now I've got my complete triangle. That's easy now because I know cos of x is adjacent over hypotenuse and tan of x equals opposite over adjacent. So I know cos of x, right, should be, cos of x should be root 7 over 4. Okay. Now that doesn't help me with x. Well, it does help me with x, but it doesn't tell me what x is. So I've got to figure out where is cos of x root 7 over 4. As soon as you see this type of question, what you're thinking you're going to have to use?
Those little formulas. The Pythagorean identities or the double angle.
Not yet, no.
No?
No. Unit circle stuff. Do you remember? You need to remember the exact solutions of certain ones.
Oh yeah.
Yeah.
I know the little triangles on the top. Like the 45, 35.
Yeah, so we know that the ones we ought to know are sine of 45, cos 45, we should know sine of 30 cos 30 sine 60 cos 60. Okay? Do you remember them?
Sine
Or-
of 45 is 1 over root 2.
Yeah.
Cos
1
of
over root
45
2.
is also 1 over root 2.
1 over root 2.
Sine of 30 is 1 over 2.
1 over 2.
Cos of 30 root 3 over 2.
Root 3 over 2.
Sine of 60 is root 3 over 2. And then cos of... Oh wait, no, 60, sorry. Sine of 60 is root 3 over 2.
Yeah, got that.
Never
And
mind.
cos of 60 is
1 over 2.
1 over 2. They should match, shouldn't they? Sine of 30, cos of 60, so and so on. Okay. Here's the problem. None of them are root 7 over 4, so what we're going to have to do...
What, like... multiply to find something that matches up to the 7 over 4?
So we need to find equivalent. It's going to be equivalent to one of them, isn't it?
Mm-hmm. What, so like, root 3 over 2?
Right, okay, so we've got the root 7 over 4, one of two ways. Pythagoras' theorem, root 7 over 4 one way, the identity one way.
Mm-hmm.
But the thing is, that is this triangle, yeah? So you've seen it from the triangle. So the trouble is, that angle is an acute angle. So what we need to do is figure out where would cos of x be an obtuse angle but with the same dimensions.
So it's like on the...
Exactly. So if you think about, this is why I was saying about the if you think about the circle, right? Can I draw on that? Right. So what we've got so far, if you think about the unit circle, cos of x is here, and that's the angle. So if we say that is the root 7 over 4, this angle is acute. So what we need to do is go to the other side, where we've got the same thing, but it's minus root 7 over 4, and that gives us, alright, and that uses the same things. Okay, next thing, cos of 2x. Well, that's relatively recent in our work. Angle identity, yeah? So in your formula booklet, cos of 2x.
Equals cos squared of x minus sine squared of x.
So based on what you did already, cos squared of x is what? Well, cos of x is root 7 over 4. So cos squared of x, or cos x squared, is root 7 over 4 squared, which is 7 over 16, minus sine squared of x is, well, you already did that,
Oh, okay.
9 over 16, which equals
2 cosine
Cos of
minus
2x.
2 over 16.
That's
Yeah.
Oh, so negative 1.
And is that the obtuse angle? Is minus 2 over 16.
Oh, then don't we have to use negative 7 over 16 then?
So
So that becomes...
we know, yeah, but what happens when you square it?
Square a negative? It becomes positive.
So remember, we could have
Oh,
used
right.
negative root 7 and it'd be, but it actually is that okay. So negative root 7 over Yeah, so square root principles. Yeah. Now that root minus 2 over 16, can we just confirm, would that be for the obtuse angle? So that would say cos of x, but this being 2x, would be adjacent over hypotenuse. If the adjacent is a negative, then we would say we've got the angle that's obtuse. Yeah?
If the what in there? Oh, right.
So remember,
right.
cos is adjacent over hypotenuse. So if we've got a negative adjacent, but also cos of 2x is a negative value, right? So do you remember what a curve, do you remember what cos of 2x looks like? As a curve is another way of thinking about it. So we've got, let's say, 180, 360, 90. So cos looks like this. Okay. What does cos of 2x look like?
It's squished in.
I like that. Squished in like that. Like that, yeah? That's cos of 2x. Right, so we've got cos of 2x is minus 2 over 16. Okay. So, where's that going to be? It's going to be down here somewhere, yeah?
Oh, it's where they cross?
So, the cos of 2x, so ignore now, we don't really want the cos of x. So here's cos of 2x. We have that value of it's minus 2 over 16, right? Minus an 8, which is quite small. So we've got all of these particular, they are the solutions, aren't they? Okay. That we could use. No.
No?
You've chosen to join us.
Yeah, sure.
Really?
Wait, so you started?
Okay, so look, so the discriminant, you know the discriminant is b squared minus 4ac. I put brackets around there. Just so let's do, what is b?
100 minus 10 minus p.
10 minus p, yeah. A is p and c is
5 over 4p.
5 over 4p minus 5.
Is that the whole of c?
Yeah, because remember it's ax squared plus bx plus c. Yeah? So you've got to have a, b, c. So that's probably where, yeah. Well, let's carry on working through it. So we've got b squared, so it's p squared minus 4 times, no, sorry.
10 minus p squared.
Yeah, so 10 minus p squared minus 4 times p times 5 over 4p minus 5. So 10 minus p squared is
100 minus 20p plus p squared.
okay, minus 4p times 5 over 4p.
Minus 5.
That's what it would be. So 4p, do it down here, 4p times 5 over 4p would actually be 5p squared.
Oh wait, the top one says 4 times p.
4 times p times 5 over 4p minus 5. So I've kept that in brackets because I've got to now expand these brackets. So I've got 4p times 5 over 4p, and then I've got minus 4p times minus 5. So that's minus 20p. So in here is in the brackets. So that ends up being minus 20p.
Isn't it plus if it's minus 20?
Yeah, but I'm doing this
Oh, you
all
can
in
do
brackets. So it's still in brackets, so I've just expanded 4p times, so yeah, just to make it clear, it's 4p times 5p over 4 minus 5. So that ends up being 5p squared minus 20p. A bit clearer like that, yeah? Right, now I've got to do the minus, so it's 100, that's alright, so I've got 100, minus 20p, minus 20p, that's plus 20p, so that's nothing. That cancels with that. And then plus p squared minus 5p squared makes minus 4p squared, which is...
Yeah, my mistake was using c as only 5 over 4p.
Yeah.
So
I think a few people did that. Okay, and then the find the values of p, so that f of x equals 0 has two equal roots. So what does that mean?
when it equals to 0. I mean, it's the b squared minus 4c.
Yeah, but the fact is two equal roots.
Must be positive.
So no, two equal roots means only one root, really, which means the discriminant b squared minus 4ac has to do what? Has to equal 0. So then what's in the square root of the formula? It's what you're expected to remember. So if you had to find the roots, you would do x equals minus b plus or minus square root of b squared minus 4ac all over 2a, yeah? If the discriminant is 0, then b plus 0, b minus 0 is the same thing. So you end up with x equals minus b over 2a.
Yeah.
Which, do you recognise the formula for that? That's the formula for the axis of symmetry.
Yeah.
But it also means there are... hang on, have I done something? Yeah, no. So, so if we've only got... That means we've only got one solution there. For the axis of symmetry is only one value, yeah? Right? And if that value, if the axis of symmetry is then on the x-axis, the vertex, you've only got one solution. Alright? So that's where the solution is also the axis of symmetry. Right? So that's what we've now got to solve. So that's, you don't have to do any of that, you've just got to remember two equal roots means the discriminant equals 0. Right? So then, because of what you've already done, that just means 100 minus 4p squared has to equal 0, which means that 100 equals 4p squared, which means p squared equals 25, and p therefore equals...
5 or negative 5.
Good, I'm glad you said that. Plus or minus 5, because it does say find the values, and too many people just put 5 as a solution. Alright. Let's have a look at this question 9 then. Same paper, paper 1. So, function has its derivative given by f dash of x equals that where k is a constant. Find f, the second derivative. So you've just got to differentiate this. So you've got 6x minus 2k.
Yeah, I was just going to say
Yeah. The graph has a point of inflection when x equals 1. So what does that mean, Alexander? If it's a point of inflection, go on then.
The second derivative equals 0.
The second derivative equals 0. So that's what we had to see in the method. So you want to be doing 6x minus 2k equals 0. So it says show that k equals 3, and this is what you have to do. To show that, you have to write that, and then go about it. So 6x, well, x equals 1. So we wanted to see 6 times 1 minus 2k equals 0. So rearrange. So 6 equals 2k, which makes k 3.
If I know this.
Okay. Same thing we were talking about before. Find f dash of minus 2. So we just do 3. It's all about being careful. Minus 2 squared minus 2 times, well, we know k is 3 now. So 3 times minus 2 minus 9. So we put that in, and then we, step by step, we might as well. So it's 3 times 4. And then minus 2 times minus 6, minus, I'm doing step by step. So it's 12 plus 12 minus 9, which is 24 minus 9. 24 minus 9 is...
I added 9 and I wrote minus 9.
What's 24 minus 9, Julia?
Sorry.
24 minus 9?
15.
15. Okay.
Are there no method marks on this one?
2 marks. Only 2 marks for that. Find the equation of the tangent to the curve at minus 2, 1. Oh, so look. So x is minus 2. Alright, okay. So we're taking hints. What do I know about the tangent to the curve of f of x?
It's a negative reciprocal.
No. The tangent to f of x.
Oh, that's the
Right.
derivative. No, that's a gradient.
So we need to know the gradient is the same, yeah?
Mm-hmm.
So that's what we're looking for. So the gradient of f of x at minus 2 is the gradient of the tangent line. Yeah?
Wait, the gradient?
Because the tangent is y equals mx plus c. Alright? So the gradient being f dash of x will give you m for the gradient. Or a if you're doing IB, ax plus b. So we need to know x is minus 2, so we need f dash of minus 2 equals m on that line. Oh look, that just happens to be part C, so that m is 15. So over here we can then do y equals 15x plus something. And how do we do it? Well, we know the tangent passes through that point as well. So when x is minus 2, y is 1. So we do something that we've done over the years, which is 1 is 15 times minus 2 plus c. Okay, so that's 1 is minus 30 plus 31. Therefore c is 31. So we've got finally y equals 15x plus 31 is the equation of the tangent.
Why did you get the 31?
Because I've got to have 1.
Yeah.
15 times minus 2 is minus 30. What do I add to get the 1? Minus 30 plus 31 makes 1.
So that it equals 0?
No, 1.
Sorry.
Yeah.
Okay.
Do you know why it's equal to 1?
So because y is 1, where
Because of
x
the,
is negative
yeah.
2.
Up there in the coordinates, I'm using minus 2, 1. So x equals minus 2, y equals 1.
Hey, wait, could you please repeat at the very beginning where the gradient is f dash of x?
Okay, so the whole point of a tangent, so let's say we've got a curve, alright? A tangent is a straight line, perfectly straight obviously, that goes through one point. So let's say that coordinate there has coordinate minus 2, 1. The tangent at that point touches that point. Just touches it, only at that point. Now what we know is, this is how, before we did differentiation, Ivan's favourite subject, before we did differentiation, this is how you find the gradient of a curve at a point, because you find the gradient of the tangent. So then, because we developed, we know if this is f of x, f dash of x is the gradient at that point. So f dash of minus 2 is the gradient at that point. Yeah. Now that is the same gradient as the tangent line. So if that's y equals mx plus c, we know from our linear functions that m is equal to the gradient. So we know for a tangent that m is the same as f dash of x at that point.
Yeah.
Yeah. So we'd already worked out f dash of x was 15, so we put that in, and then we just have to work out the next bit.
Okay.
Okay, so then we've got to do, given that f dash of minus 1 is 0, explain why the graph of f has a local maximum when x is minus 1. What do you reckon? Well, what do we know about when the gradient is 0? It's a turning point, which means the gradient is 0. It's a turn. Now, a turning point is either a maximum or a minimum. Okay, so I'm just going to move this down. So we'll say, was it f dash of minus 1? So f dash of minus 1 we know is equal to 0. That gives us a turning point. So we know at some point on f of x, our curve is going to have a flat bit. Now, that is when x equals minus 1. It's going to have a flat bit. Now, it could either go down like this to that point, or it could go up like this to that point. Which one is it and why? So it could either be a maximum or it could be a minimum. And they are saying what in the question? They're saying it is a maximum. So we're looking at why?
If the gradient is positive, then it was in a positive region, but it was increasing.
Well, what's the evidence? What's the thing that's been in the question? What we've been working on? So we know f dash of minus 1 is 0. What was the other thing we've been working on? Previous question, part B or whatever.
F dash of negative 2.
So that is to the left, yeah?
Yeah, it's 15.
F dash of negative 2 is what?
15.
15. Therefore, we have a positive gradient going up, going to 0 gradient, and the only way that can happen is if it's a maximum. That's one way to put it. Okay?
Check it on the calculator?
So if we, well,
But we don't have calculators on this paper.
no, so it's not use a calculator. So what we ought to do, just to be 100% sure, okay, is to work out something to the right-hand side. So let's work out f dash of 0, so to the right-hand side. And f dash of 0, well, we know what f dash of 0 is, don't we? Because if that's f dash of x, what's f dash of 0? I'll let you think.